Hi, in this video we are going to talk about the mixed and plug flow reactors and their size requirements for single reactions. We are going to focus our discussion based on the first and second order reactions over here. For a given duty or for a given task that you want to achieve using the reactor, the ratio of the sizes of mixed and plug flow reactors will depend on certain factors. What are these factors? One big factor is extent of reaction. Okay, so the extent to which you want the reaction to proceed. The next factor comes the stoichiometry involved. Of course, this is very important. And the third factor comes the rate equation. Okay, so these are the very deciding factors for the sizes of mixed flow reactor and plug flow reactors. Okay. Now, if you want to compare for a very general case, what you would do? You would do to compare these performance equations for these reactors. So, if you remember when we were talking about the steady state mixed flow reactor and plug flow reactor, we had deduced the uh, performance equations. So, for the mixed flow reactor, the performance equation was given as P by Fa0 equals to tau by Ca0 equals to delta Xa by minus Ra for any volume ratio. So let me just explain these terms. We are just simply considering a reaction A gives products. V is the volume. Let me write Vn to signify the mixed flow reactor aspect. Fa0 is the initial molar flow rate. Tau is the space time. Again, here let me write tau in to highlight the MFR aspect. Ca0 is the initial concentration of A. Del XA is the difference between the initial and final conversion of A, and RA gives the rate expression. Okay, so this is for MFR. For PFR, what do we have? Let's write the performance equation for the PFR now. So for a PFR, V, let me write small p, Vp by Fa0 equals to tau p by Ca0 equals to integration from 0 to xaf. Just make it more clear for you. Xaf dxa by minus r for any epsilon a. So if you consider for the plug flow reactor, obviously you need this differential term because you are dealing with the differential volume of the reactor when you are deducing the performance equation. So for a detailed understanding about that, I suggest you to go through my other lectures on this topic. As of now, to compare between the sizes of MFR and PFR required, all you need to do is take the ratio of these two expressions. Okay, so that will give you the understanding what will be the size ratio for these two types of reactors, these two types of flow reactors. Now let us just study this in detail for the nth order kinetics. So let's say you have the rate equation minus Ra as kCa to the power n, and this n is varying from 0 to 3. Okay, this can vary. Okay, I shouldn't write it like this, I should rather write it as anywhere between 0 and 3. Okay, so it can be some fractional order also, that is fine. Now how do we go about this? So just taking cue from these performance expressions that we have already written. So we have the performance equations over here. I'm just going to replace this minus RA equation, minus RA expression in these two equations and get the final form. So in case of one mixed flow reactor, the tau m becomes Ca0V by Fa0 for the mixed flow reactor equals to Ca0Xa by minus Ra, which in turn is equivalent to 1 by K Ca0 to the power n minus 1 multiplied by Xa 1 plus epsilon A Xa to the power n divided by 1 minus Xa to the power n. So here I have not stuck to the understanding that this is only a constant density system. I have taken it that epsilon A is not equals to 0. So accordingly this expression has been drawn. The same thing when you do for PFR. So tau P, that means Ca0V by Fa0 for plug flow reactor. That becomes Ca0 0 to Xa dxa by minus Ra, which becomes equivalent to 1 by K Ca0 to the power n minus 1 0 to Xa 1 plus epsilon A Xa to the power n dxa divided by 1 minus Xa to the power n. Okay, if you now divide these, then the final expression that you will get is something like this. So tau Ca0 to the power n minus 1 for mixed flow reactor divided by tau Ca0 to the power n minus 1 for plug flow reactor equals to Ca0 to the power n multiplied by V divided by Fa0 for mixed flow reactor divided by Ca0 to the power n multiplied by V divided by Fa0 for a plug flow reactor equals to, on the numerator, Xa multiplied by 1 plus epsilon A Xa by 1 minus Xa to the power n for mixed flow divided by integration of 0 to Xa 1 plus epsilon A Xa by 1 minus Xa whole to the power n dxa for plug flow reactor. This is the expression that you will obtain for a general case. Now if you just put let me write this over here, if epsilon A equals to 0, that means a constant density system is now being considered, then tau Ca0 to the power n minus 1 for mixed flow divided by tau Ca0 to the power n minus 1 for plug flow equals to Xa by 1 minus Xa to the power n for mixed flow divided by 1 minus Xa to the power 1 minus n minus 1 divided by n minus 1 for plug flow, and this expression is valid for n not equals to 1. Okay, if n becomes equivalent to 1, then let me write it like this. So if n becomes equivalent to 1, then this becomes xa by 1 minus xa for mixed flow divided by minus natural logarithm of 1 minus xa for plug flow. This is for n equals to 1. So this gives the size comparison for mixed flow and plug flow reactors for different orders ranging between 0 to 3. Now, obviously, these expressions look very complicated, but what are the key takeaways or what do we understand from this expression? So, just going to list those down, and you can note it as observations that are obtained by various studies which have been conducted throughout the last 150 years of research, and then coming to these expressions. So, the key understanding is for a given duty or the task to be completed by the reactor, and for all reaction orders that are positive, so n being positive, okay, the mixed flow reactor is always larger than the plug flow reactor. Okay, also ratio of volume of MFR to PFR increases with increasing order. This is one of the key points that you need to remember when you are talking about flow reactors. The next observation that we have is if XA or the conversion is small, the reactor performance is very less affected. So I am just writing not affected much by flow type. Okay, it's not affected much by the flow type. The performance ratio increases very rapidly at the higher conversion values, and therefore in higher XA ranges you need the proper representation of the flow. Otherwise, for very small XA, whether you use MFR or PFR, the reactor performance is not much different. Another important thing is the density factor. So, if you consider the density factor varying during the reaction, it definitely affects the design. Okay, but when it comes to the difference in flow type, uh, density factor is secondary, or it is not that much important. The first importance is given to the flow type involved. So out of these three observations, okay, let me write down the last one properly. So density variation during the reaction affects design but is of less importance than difference in flow type. Okay, so the this is the like three main observations that we get from all of those a bit complicated looking reactions, but you know how to find them. All you need to do is get the ratio between the performance equations for the two types of reactors. The main understanding is that if your reaction order is positive and you have a certain task to be achieved by the reactor, then the MFR volume will always be larger than the plug flow volume. So that is one thing, and the other thing is that if you consider the ratio of volumes, then the volume ratio increases. The volume ratio of MFR to PFR increases if the reaction order is increasing. Now, if you have reactions with a known rate expression, but that is arbitrary, it's the expression is not like a general form of the nth order, then of course you have to find the performance and the size requirements using some other technique, not just by reducing a general expression. So in that case, the best thing to do is to go with the graphical method if you have the experimental data or the reactor data, sorry, reaction data, my mistake. So if you make a plot of conversion on the x-axis and 1 by minus RA on the y-axis, and you get a curve like this. So this is your initial conversion, and this is your final conversion, XAF. Okay, initial conversion being XAI, and this is any rate curve. Okay, then the area under this region is going to give you the, let me just demarcate this area. So this total area is going to give you tau m by Ca0. So that gives you the understanding for MFR. Okay, if you have a PFR, let me just draw this diagram again. So you have XA, you have 1 by minus RA on the y-axis, and this is your rate curve. This is XAI, this is XAF. Then the area, okay, slight mistake from my side. Yeah, so the area, okay, I'm still unable to match the lines, spare my drawing skills please. So the area under this region, that area gives the tau p by Ca0, that is for a plug flow reactor. Okay, so you can find the ratio of the shaded areas, and then that gives you the necessary ratio for space time, and then you can ultimately understand which reactor you want to use. Now this rate curve is that I have shown over here, and this is also there in the Levenspiel book. This rate curve caters to a very large class of reactions. Okay, mainly this is very suitable to describe reactions whose rate decreases as it goes towards equilibrium. So all nth order reactions are covered in this rate expression, rate curve that I have drawn. Now for such reactions, you will always see that MFR volume is larger than the plug flow reactor volume. So this understanding stays with us for nth order reactions. So with that, we can now compare between the size requirements of the mixed flow reactor and a plug flow reactor for a given reactor duty and with positive reaction order. That is it. Thank you.